So today we are going to use our knowledge of transformations. We're going to apply it to square root functions. Yesterday we practiced the skill of combining the transformation function with the equation of the parent function. So in this case, this is a little bit of an extension just to see what you can do here. Emma, can you shut the back door there for us? Thank you. So this is just a bit of an extension of what we did yesterday. So yesterday, we were working with the parent function x squared. Now I've given you the parent function square root of x. So does anyone have an idea of what the final equation of g at x should look like once we combine f at x and g at x? Any guesses?
Take out the f and then square root it.
George?
G bracket x equals -2 to the square root of bracket -1/3 bracket x plus 6 bracket, and then -5 outside the square root.
That's right. So this is what our final transformed equation should look like. Yesterday we talked about how like the f part of this represents like the name of the function here. So the f at x part of this, we want to remove the f part and then replace it with the operation of the parent function. And the operation of our parent function is root x. So you'll basically notice that the k and d value are underneath the root here. And then the a and c value are on the outsides of the root. Okay, so the idea is that basically what we're doing is we're dropping this out and we're replacing the operation of the parent function, which in this case is a square root, over top of this entire bracket. Okay, so that's how we combine the two of them. So that's basically what we're going to be working with today is the square root function. So over here, I have just a reminder for you guys of what those points were that you guys graphed in that package. So you guys did that investigation package, you graphed 3 functions. Those are our 3 parent functions that we're going to be working with for this unit. So a good set of key points to choose for the square root of x function is 0, 1, 4, 9. Can somebody tell me why I would choose those specific x values for this function? Lauren, what do you think? They are perfect squares. So what happens when I square root these then? We get whole numbers, right? What did you say? That it's easy. So certainly I could choose 0, 1, 2, 3, 4, 5. But when I square root something like 3, I'm going to get a decimal. So if we want whole numbers, we'll choose perfect squares. And then I square root them to get the y's. So square root of 0, square root 1, square root 4, square root 9 is 3. Okay, and then just a reminder of what this function kind of looks like. It looks almost like half of a quadratic on its side. So it's like half a curve here. In our function from yesterday, we did the x squared function yesterday. I chose -2 to +2 as my key points. Why wouldn't I choose negative x values for this function? What's that? You can't square root a negative. So there are some restrictions on this function. The domain only goes from 0 and forward, right? It only goes 0 and positive numbers. I can't square root negatives. So if you choose x values for this, you need to ensure that those x values are 0 and above, greater than 0, or equal to 0. Okay, so those are the key points that we're going to be using for today's lesson. So we're going to do a couple questions here. Okay, so first things first, let's identify A, K, D, C. What do we have? Charlie? Great. Perfect. So let's just discuss verbally, what does an A value of 1/2 do to my graph? How would we express that in words? Charlie? Yep, perfect. Vertical compression by 1/2. Okay, so let's just make a little prediction here. Do like a little step-by-step sketch. So here's the parent function, looks something like this. My first thing if I have an a value of a half, vertical compression, imagine you take your graph and do this. I almost did horizontal. Imagine you take your graph and do this. We're going to have something kind of like this, right? It's going to become kind of like skinnier. And then c of positive 1, what does this do to our graph? Lauren?
It would go up by 1.
Up 1. So we'll take that blue graph and just shift up 1. And this is kind of what our final function should look like. So this is what we expect to get once we do our points. Okay, so I told you guys yesterday, we're basically just going to repeat the process of what we've been doing for the squared function, x squared. We're going to repeat it with the square root of x. So our key points for our parent function, this is now telling us you're starting with the square root of x function. And we listed the key points above. They are 0, 1, 4, 9, and their corresponding points 0, 1, 2, 3. These are now the points that I'm going to use to do transformations to. Same way that I did them to x squared, but now the parent function is different. Okay, but I'm going to calculate the transformations in the same way as I did yesterday. Okay, so our formulas, let me just grab a different color here. Okay, our formulas, if you guys remember, are reciprocal of k times x plus d and ay plus c. So who wants to try to set up our formula for us here, or one of our formulas? Ethan?
The x value is the x.
Yes, very good.
Wow.
X is x. Ethan, you're so smart. How about y? George?
Would be 0.5 y plus 1.
Yep, so you can use 0.5. If it were something like a third, we'd probably want to keep that as 1 over 3 because it can't be expressed as a decimal. But if it's something like a half, if you want to put the decimal, that's fine. I'm going to keep it in fraction form here just so that we can see the a value as it looks in the equation. So 1/2 y plus 1. Okay, so you'll notice that I just recopied the x's. Okay, the x's don't change, so I recopied them here. You're going to take each of these y's, and you're going to half them and add 1. Okay. So we're going to make sure that our scale of our graph works to accommodate both the parent function and the transformed function. One thing that we should know as well is that our x and y axes can have different scales, right? So I need to make sure that I can get up to 9 on my x scale, so we'll probably do 1s for that one. So we can fit that. Our y's, all we really need to get up to is a maximum of 3, so maybe we'll do every other here. We'll go by 0.5s. Okay, the big thing is we want to make sure that both the parent function and the transformed function fit together on this graph. Okay, let's sketch the graphs. Or not sketch, but actually plot. Okay, so this one's the parent function. I'm just graphing x squared, or square root of x, sorry. And we're going to label. And there's your transformed function there. And we also want to label this one with the final transformed equation. So I want you guys to think about that for a couple seconds, see if you can figure it out. How do we combine the parent function, square root of x, square root of x with this transformation function, and then we're going to label it on the graph here. So g at x equals what? So what should the equation look like?
Yes, I think the 2.5 is wrong.
Half of 3 is 1.5.
Isn't it half of 9?
No, we're doing the y's over here.
Okay, that makes sense.
It's good that you're checking though, because sometimes I do
Nothing.
my mental math wrong. Okay, what should this equation look like? No guesses? So this should look like half square root x plus 1. Right, we drop this out and input the function here. And the plus 1 should not be underneath the root. It should be outside the root. So make sure your root doesn't cover the plus 1. Any questions on that one? We're okay? Okay, let's go to the next. Okay, AKDC, what do we have, guys? George.
A is -1. A is 1 over 2. B is +1.
So when we state K, we're actually going to state it as 2. D, we flip the sign. And then when we think about the transformation, we want to think about K as like a half. So that would be horizontal compression by a half. Okay, we're going to do a little prediction here. So here's our parent function. What does the first value do here? What does the a of -1 do to our graph? Zach?
What the?
Vertical or horizontal?
Vertical?
Vertical, yeah. So we'll flip it down.
Yeah, that.
That's the a value. K value of 2, we already said that. This is a horizontal compression by a half. So imagine you take your graph and you push it inward horizontally. It's going to kind of look like something like this once we do
So
that
what's
K value.
it?
Horizontal compression by a half. Doing this. Okay, and then D value of 3, what does this do? Lauren?
It goes to the right 3 spaces.
Okay, so take the red graph, 1, 2, 3 over, and we're going to have maybe something like this. So that will be the third and final graph. Okay, so if we do our calculations correctly, we should expect that our graph will look somewhat like this. Was our prediction pretty accurate from our last one? Yeah, that was actually pretty close. Okay, let's do the transformations of the points then. Okay, we'll just do it below here. Okay, so starting with the parent function. Oh, sorry, wrote the y coordinates accidentally. Okay, and transformed function. What do our equations look like? Lauren?
It would be 1 over 2 x plus 3.
Very nice. She's right. Who wants to do the y side for us? Charlie? Sorry. Yeah, so just -y is really all we have to write. Sorry, George, that was my fault. I looked at you as if I was going to tell you to go, and then I chose Charlie. Yep. Okay, take your x's. We're going to half them and add 3 to them. And take your y's and multiply them by -1. So the y's are basically just going to switch sign. Okay, notice as well that I'm just trying to keep my points together here so that I don't get confused as to what x goes with which y. So if you need to, you can draw some horizontal lines as well to kind of keep the x's and y's together properly. Okay, one thing that you will also notice here, guys, is I'm being mindful about where this point right here gets transformed to. That's actually the starting point of my other function. So this function only continues forever in one direction, and it has a distinct starting point. So this starting point at 0, 0, it actually gets transformed, and that new starting point of our new function is at 0, 1. So I'm always making sure that I take note of what this point gets transformed into, because this is going to be the starting point of my new function, and the opposite end will have an arrow off to the end. Okay, so this is where the function starts. Okay, I think we'll do maybe like a similar scale here. We'll have 2, 4. Let me just zoom in here so you guys can see a little bit better. Aw, so kind. So we'll do just like a similar scale as what we did last time. Okay, graph your parent function. I'll call it f at x. And graph your transformed function. Oh, I'm going the wrong way here. I graphed 2.5. Trying this really badly. There we go. Okay, and then you guys are also going to decide what our final equation should look like here for this function. So what will the label look like? Okay, notice my green point here. It's at 0, 3. I'm making sure that there's no arrow that goes off of that end. It only goes off the opposite end. So over here, we can continue forever toward infinity. So what does the label look like on the equation here? So how do I combine this with root x? Ethan? Yes. So the 2 and the x minus 3, the k and the d values go underneath the root. A and c will stay on the outsides. In this case, c is 0, so we don't have to worry about that. But our a value should be out front here. Okay, so that should be what your label looks like there. Any questions on this one, guys? Does this look similar to our prediction? It looks somewhat similar. Our scale is a little bit different on this one because we made the y's larger. Or I guess smaller. Okay, can I scroll? We're all good? Okay, AKDC, what do we have? Go ahead, Charlie.
A is -2. D is -3.
Lovely. Okay, let's make a quick prediction here. Here's our parent function. A of -2, what does this do to our graph? It's a vertical stretch, and the negative part? Reflection. Okay, so here's the reflection, and then if we stretch it, if we take it vertically and we stretch it out, it's going to look kind of maybe more like this, right? Something like that. Okay, D as -3. Lauren?
It goes left.
1, 2, 3, very nice. So something like this now. And C of -1? Down 1, so take your blue graph, shift her down 1, and now it looks like this. This will be our final graph, something like this. Okay, a couple people, I don't know if it was from, I don't think it was from my other class, I think it was from this class. A couple people were asking me, like, do I have to do this prediction part? I'd like you guys to practice that just because I may ask you some questions, like show me a step-by-step sketch of what this equation or what this graph would look like after each transformation and then what the final looks like, right? So just exactly what we did here. Show me step by step what each of these transformation does and then label the final graph once you get there. So make sure that you know how to sketch each individual one. And then when we actually calculate, we'll do all the transformations together in one calculation. Okay, so parent function is root x for this one. So using those same parent function points from above. And then we're going to set up our equations here. So what should our equations look like with these values? Yep. Perfect. Lauren, you want to do the other one?
-2y minus 1.
Very nice. Okay, take each of your x's, subtract 3. And take each of your y's, multiply them by -2, and subtract 1. Whoops. Tuesday, that's a lot of math. Multiplying and adding is so hard, eh?
Yeah, that's a rough life.
Okay, so we want to make sure we can fit both of these graphs on our graph above. Notice that your y's need to go all the way up to -7. So I think we'll just choose a scale, an x and y scale. We'll go by 1s on each of them, just so that we can make sure that we fit it all. Okay, graph your parent function. Okay, it looks a little bit different than the ones that we just did because the scale is different. Oops, root x. Okay, and then we're going to graph each of these points here. So -3, -1, -2, -3, 1, -5, and 6, -7. Notice as well where your 0, 0 got transformed to. That's the point -3, -1. So that's actually this point right here. On the other end of this function, I will have an arrow, but this is the starting point. So I shouldn't be going any further than that red point toward the left. Okay, so should look something like this. How was our prediction? Not too bad, right? Okay, and then final thing, label. What does this look like when we combine this function and this function? No one? Anyone? Charlie, you want to try? And -1 under the root or after? Very nice. So just like this. X plus 3 is underneath the root, A and C are on the outsides of the root. Good job. Lovely. Okay, you guys try number 4. Start with locate your A, K, D, C, do a little prediction, and then see what you get for your points, okay? I'll start taking it up in a few minutes, but you see what you can do with that to start. All right, guys, so this is what your prediction should look like if you did like your individual sketches here. So A, K, D, C, that's what your prediction should look like.
Up on the prediction, I'm gonna lie.
And then we'll take up the points in a second, okay?
Well, the prediction has one thing, right?
Great. So this is what we should get for the tops of our equations, and then you're just going to calculate out your points here. So take a couple seconds to plug each of those in.
Why is it
Because we do the reciprocal of the k value. So what's the reciprocal of 1/2? Yeah. And there's a negative there, right? So we don't switch the negative. It's not negative reciprocal, it's just reciprocal. Okay, so what'd you guys get for your points? Does someone wanna, did you guys get your X's and Y's yet? George, what'd you get?
I said for x, it's -7, -9, -15, and -25.
Great.
And for y, it's 1, 4, 13, and 28.
Ooh, I got 7 and 10.
1, 4, 7.
Maybe you did 4 and 9 accidentally instead of 2 and 3. Okay, so that's what your points should be. Again, we're taking just special notice of where the 0, 0 gets transformed to. So when we see our graph, -1, 7 will be the starting point that we work off of, and then arrow on the opposite end. We also want our x's to fit all the way up to -25. So we need to make a scale that's going to fit that, or sometimes if your scale doesn't fit that, it's okay to maybe just cut off that last point. So for us, maybe if we graph like up to -15, 7, that might be sufficient just so that we don't have a hard time graphing the parent function here.
Like big numbers on the test like this.
You might have to cut off maybe like the one like last point there just because you can't fit it. Or again, you can choose your scale, right? So you can choose a scale that works to fit that. So I guess I guess we can try to fit all 4 points. That should be okay. And for y's, we just need to make sure that we can get up to 10. So for the y's, I think we can go by ones. And then for x's, we need to get up to 25. So maybe if we do 5, 10, 15, 20, 25, that should work. Okay, so I'm going to go by 2.5s. Oh. Okay, so the parent function is going to be a little bit squished here because of our x scale. So do your best. You can even graph 25 and 5 here, and 16 and 4, since they fit on our graph. So there's our parent function. Okay, and then graph your points of your transformed function. So -7, 1. That's the starting point. -9, 4. -15, 7. Oh, that was 8. And -25, 10. Here we go. So this is the side with the arrow, and then it stops at -1, 7. So make sure you don't go past this point. How do I label my graph? George?
Is it 3, the square root, -1 over 2, bracket x plus 7, bracket plus 1. Outside of the
Yes, perfect. Okay, I'll zoom in a little bit there so you guys can see it. Okay, any questions so far? We're kind of just repeating that same process on a new set of points. And we just want to be mindful with this parent function in particular where this point goes, because that's the starting point of our function. And then you'll have the arrow on the other end. Okay? Okay, last question. You guys may have seen some questions like this in your homework yesterday. It tells you what the transformations are in words, and it asks you to create an equation from those transformations in words. Can I scroll off of this? Is everyone good? Okay, so let's take a look at the last example here. So it says, create an equation using the parent function root x, which performs the following transformations. Vertical stretch by a factor of 3, vertical reflection, horizontal compression by a factor of 1/2, shift left 5 units, and shift up 10 units. Okay, so can somebody pull out some pieces of information here and tell me what we know about A, K, D, C? Give me one, Charlie. Very nice. A is -3. The vertical reflection makes A negative, and the stretch is the 3. Perfect. George, can you give me another one?
K is 2.
K is 2. Very nice. Good job using the reciprocal there. Lauren?
D is -5.
D is -5. That's right. And C is 10. Yeah, that's good. Okay, so when we put them into our equation, this is kind of what it's going to look like. The A and the C will be like on the outsides of the root. And then we'll see the K times X minus D inside the root. Okay, so you're just going to fill in from there. So -3 We already did the reciprocal of k, so we're going to use it as 2. And then when we plug in the d value, what's going to happen?
Opposite. It's opposite.
Yeah, so it'll be like x plus 5, right? Because when I plug in a negative into a negative, I'll have negative and negative. That makes positive. Okay, so plus 5 in there, and then we'll have the plus 10 on the outside of the root. So there's our equation. Okay, if your parent function was x squared, it would be similar, except instead of the root, you would have brackets and then a squared on the outside of k and d, right? So same kind of idea. Any questions with that one? We're okay? Are you guys starting to get the hang of it a little bit? Yeah? Okay, perfect.